Hello, my name is Boukerche Kantarci. I'm an associate professor at the University of Ottawa and the founding director of the Next Generation Communications and Computing Networks Research Lab at the University of Ottawa. I'll be presenting our paper titled Self-Organizing Feature Map Integrated Knowledge-Based Deep Network Against Fake Crowdsensing Tasks. And this work is in collaboration with Dr. Simsek and Professor Boukerche, both with the University of Ottawa. And this paper is in IEEE Global Communications Conference, IEEE GLOBECOM 2020. Let me quickly jump into our motivation in this study, and I'll talk about the details of our work and our contributions. Fake tasks. So the fake tasks, or as we call the illegitimate tasks, the motivation for those tasks is twofold. So they aim to drain the batteries of these participant devices by clogging their sensing, memory, and processing resources. And also they aim to clog the sensing servers in the mobile crowd sensing platform. So we need to identify these fake sensing tasks submitted to the mobile crowd sensing platform. So we have been working on this topic for a while, and as you can see here, these are the class-specific settings of the illegitimate and legitimate tasks in a mobile crowd sensing platform. And as you can see here, a majority of the fake tasks arrive during the peak hours, and majority of them last longer than the legitimate tasks, and majority of them drain significant amount of battery power from the participant devices. Well, if they have these characteristics, they should be able to be easily identified. That's one would ask actually at the first place when they see these characteristics. But these fake tasks are also modeled and submitted in an intelligent way, so to disguise them in an environment where legitimate and illegitimate tasks coexist. So a part of our work also includes anticipating these threats and modeling them in a way that they are submitted by being disguised in that environment. So considering that they are also intelligently modeled, we need to identify them by introducing intelligent solutions. So this is mainly what we have been using to identify these type of tasks. All right, so at the core of this framework, we have a model, a machine learning based model, which can vary from one paper to another paper. So we have used different techniques here to detect these types of attacks. So here you are seeing now a deep neural network which has 10 inputs, and those 10 inputs are from the features of these tasks. So the location information, the timestamp for the submission of the task, the duration of the task, remaining time of the campaign, and the required resources and the coverage of the task, and whether or not the task has been submitted during an on-peak hour, and where in the monitored terrain the task has been submitted. So these are the features that characterize a task, and these inputs are fed into our detection framework here, which is a deep neural network in this study. So that is a base model here. But as we change the scheme here, well, we can have slight improvements in our detection performance. But instead of those slight improvements, we need to make some substantial boosts in the detection performance of the machine learning based detection. So we need something beyond that. That's what we are trying to address in this study. So we introduce 3 different improvements on top of the machine learning backed detection of the fake tasks. Right. So to start with, now this is, as I said, how the prior knowledge information is generated. So we have a self-organizing feature map here, and the output of the self-organizing feature map is provided as an input, as an additional input to our detection network here, which is a deep neural network, as you can see at this point. Okay. Now, the first improvement, as I was mentioning earlier, is based on feature selection. So finding the best inputs here for the for this detection. Now, we use two feature selection mechanisms here. First one is a wrapper method, which is sequential feature selection. The other one is a filter method, which is relief algorithm based feature selection. So by running these two algorithms, we aim to find the most important features in this detection framework. So the most important features that characterize a task's legitimacy. Okay. Now, what we are doing, by the way, for the sequential feature selection is we are using a support vector machine, as you can see, and the selected features are from 3 to 7. Okay. So the prior knowledge information is generated by a self-organizing feature map, as I said before. So it has, here in this figure, it has 16 neurons. Okay, it's a 4x4 network. So this is what we have in our training phase. Okay, so over 16 clusters here. That's what we have in our network. Okay, and in the test stage, this is what we found in each cluster. So these are the fake tasks, and these are the legitimate tasks. Okay. So the yellow denote the legitimate tasks, and the red denote the fake tasks in these clusters, right? Okay, so we have now the first improvement, which was the feature selection. Now we have the prior knowledge generation by the self-organizing feature map. Okay, now let's see how the feature selection-based improvement affects the performance. Okay, so this is the deep neural network performance with 10 features. So that's the performance by using the 10 inputs, actually, as I presented earlier. So this is the performance upon using sequential feature selection. And this is the average accuracy performance upon using the relief-based feature selection, as you can see. Okay. So the best performance is obtained with 4 features selected based on sequential feature selection. Okay, now our first improvement is here. Okay, right, and this is our accuracy level. All right, now the second improvement is based on the generation of the prior knowledge inputs, right? And the prior knowledge is generated through a self-organizing feature map. Okay, so this is the performance of our deep neural network. Okay. Now, we need to vary the number of neurons in our self-organizing feature map. So we use different combinations here, from 2x2 to an 8x8 network. And the best performance, as you can see here, is obtained when we have 49 neurons in our self-organizing feature map. Okay, so this is our second improvement. Now, we need to also understand the impact of the hidden layer neurons. Okay, so let's see how this affects the performance, the accuracy performance of our overall framework. Now, this is the average deep neural network with prior knowledge inputs performance. And this is the average deep neural network with prior knowledge input performance as we have observed. And these are the performances in each run when we have the hidden layer neurons, or 10 neurons per hidden layer. Okay, and here we have 15 neurons per hidden layer. And as you can see, well, when we have 10 neurons per hidden layer, we can achieve higher accuracy in our detection. Okay, so this is our third improvement. Okay, so now we know how many features we're going to be using, and we know the impact of the self-organizing feature map, and we know that 49 neurons in the self-organizing feature map provide us the best results, and we also know that 10 hidden layer neurons in our deep neural network will give us the best accuracy performance. Okay. And of course, here we are checking the number of features for the self-organizing feature map as well. And the best performance here is under four features. So when we implement self-organizing feature map with 4 features, we get a better performance compared to the accuracy performance when self-organizing feature map was implemented with 2 features. And those 2 features were, by the way, let and long. In addition to that, if we have the coverage of the task and also the grid number in the monitored terrain, well, this provides us a better prior knowledge of the task characterization. Okay, compared to our first base scheme, what is the improvement here? Well, the feature selection provides around 8.6% improvement in terms of the accuracy. Well, when we introduce the prior knowledge input, well, the improvement here, the accuracy improvement, is close to 9.5%. Okay, a little bit less than that. Well, when we also optimize our hidden layer neurons, the number of the hidden layer neurons in our detection model, well, the third improvement further boosts our detection accuracy. So more than 9.5%, a little less than 10% accuracy improvement. Now, to conclude, we have introduced 3 improvements on top of the deep neural network-based detection of the fake tasks here. The first one is the sequential feature selection mechanism. The second one is generation of the prior knowledge input through a self-organizing feature map. And the third one is determining the number of hidden layer neurons for our detection architecture. And in the third improvement, as you have seen in the previous slide, the accuracy performance has been improved by almost 9.74% when compared to our baseline approach, which was purely based on the classical deep neural network-based detection model. So this concludes the presentation. Thank you very much. I hope you enjoyed it.